There we go. So we are now being recorded. All right, so I'm gonna get started because every minute counts because you don't want to lose your money. The rolling fees and whatnot, we gotta get every penny out of this. All right, so the first thing I'm gonna do is to give you a warm up, on topics that we have talked about already. And then there's one big long proof that I don't need you guys to read it, nor am I gonna go through that very carefully. But I'm just gonna show you that it is there for those people at least. And then we'll start with new topics. All right, so today's lab is gonna be about addition. And you guys might think, I've been adding numbers, for the past 15 years, 20 years, and for some of us, like a few decades. So I know how to do that already. Well, that may be the case, but what I'm asking in the lab is whether you understand the material related to this class. So that has to do with the structure of multi-digit addition, and not just whether we can add in base 10 or not, because we have to generalize the structure of any numbers and then be able to abstract the structure and then reapply the structure to only base 2. So that's kind of the roadmap of the binary addition module. So we'll start with something like this. This example here. If I know that 6 plus y, the whole thing, mod 8 is 3, do I know what y is, or do I have a way to figure out what y is? And I'll give you one additional clue. Y can only be from 0 to 7. So that really limits, right? How many possibilities there are. So how would you find the answer to this question? This is arithmetic.
8 plus 3 minus 6.
Right?
8 plus 3 minus 6.
8 plus 6 minus 8.
8 plus 3 minus
8 plus 3. Yeah,
8 plus 3 minus 6.
That would be correct. So that's the way to find out the value of y. Now, what is the other way you can do it? You can do it by brute force, because we know that y is an integer and it is between 0 and 7 inclusively. Just try out all 8 possibilities until you find the one that matches. Okay, I would not suggest that way, but it does work. Good thing, there's only so many integers between a certain range, unlike real numbers, because there's an infinite number of real numbers between any two real numbers that are not the same. All right, so that addresses the first thing. The second one is we have to be familiar with the rows X, Y, Q, K, and S. So if those letters are completely foreign to you today, that means you might need to review the content from Tuesday, because the lecture on Tuesday specifically talked about those 5 rows when I performed multi-digit addition. And I have proof, I have evidence, to prove that I talked about that. Let me switch to that evidence, which is actually also a segue to something that I want to show you. See this? That's what I talked about on Tuesday. So you might be asking, but how do I find that video? There are several ways. The first one is to go back to the class. Okay, so I'm going to open a new tab here. This is why I end up with a bazillion tabs in my browser. So if you go back here, you go to the announcements, and I believe that for every single recording, I disclose the recording, and maybe not for that one. But I think I also mentioned, somewhere in here, read and lecture recording on YouTube. So that is telling you that the other way to find the recording for this class is to go to YouTube, because I would download it from Zoom and then re-upload it to YouTube, because YouTube does a fantastic job at closed captioning. And once things are closed captioned, I will show you something that is really cool. It might be beneficial to some of you, it may not be, but it is up to you to choose whether to use it or not. So I turn on closed captioning. Can you guys all see CC being underlined with a red line? Okay. And then you can go to settings. And then you can go to subtitle and you click on this button here and you can do auto translate. So what it's doing is it's auto translating the closed captioning. And you can translate that to, I can only understand, Chinese traditional. So now when I play the video, it is now going to present the closed captioning in Chinese. So that's one way for those of you who who want to review the material, but you think okay, but I want to read the closed captioning in my native language. This is one way to do it. I do this a lot when I watch Japanese anime because I cannot stand the dubbed versions. So I always have to go for the sub version. So I know it can be done. I know you can still enjoy the content of the anime, not so much you guys really enjoy the lectures, but I know the content is still there. So there you go.
Subtitles are always going to be better than dub.
Yes.
What?
You like dubs? So if anyone wants to do the dub for me, you're more than welcome to do it. So there you go. So my channel name is Some Profs. Okay, so if you go to Some Profs, you will find the recordings or the videos, and these are all sorted in reverse order. So that means the most recent upload, because it's not recorded on the fly, is going to be up front, and then the older ones are down there. You just have to scroll to find the older ones. So do we have any questions about the recordings? Okay, no questions. The recordings can be very useful because if you just find one particular picture or diagram to be particularly useful, freeze that frame. Okay, use your snipping, screenshotting tool. Just kind of crop that picture and then put it into your own notes. I mean, that's a quick and easy way to extract the content of this class, whatever is on the projector, into your own notes. So I would highly suggest you guys look into this as a resource. So let me close that because I don't need that anymore. All right, so that said, now we go back to this thing here. So the rows X, Y, Q, K, S are important. It is going to be needed for today's lab. So for those of you, I hope nobody, okay, is thinking, I really do not know what those rows are. It's okay. There's still enough time in the lab to read the modules. And yes, the reading modules are intended for you guys to all read, and it is a necessary component of this class. Just as the lecture is also a necessary component of this class. You cannot do one or the other, you have to do both. Okay, because the reading material actually has all the details. So when I present the same material in class in the lecture, I'm actually going over, maybe in a faster pace. And if you guys have questions, I can answer those questions more interactively. That's the purpose of the lecture, is to be more interactive. But the bulk of the material is in the modules. So the reasoning, the equations, the definitions, those are all in the modules. All right, moving on. So the same thing goes for the R and the C functions. The C definitions are in the module already. And so I encourage you to know where to find them. So this is also a good time to kind of talk a little bit about taking notes. So if I were taking this class, knowing that there are so many notations, definitions, and so on and so forth, I would set aside a section of my notebook just for definitions. So this way, if I ever need to look up definitions of symbols, of functions, of whatnot, there's one centralized place to find them. And for those people who are kind of thinking, but Tech, why don't you organize all of those things for us and present it in your own material? I have to say, that's not my job. It is your job, because if I give you that, then you don't have to do it. And the process of going through that to extract the definitions, to extract the key points, the important topics and whatnot, that is what is helping you to understand the material. All right? Because in the end, it is not the knowledge that is going to be important. It is going to be how you can problem solve that is going to be important. In the age of AI, you have to convince the potential employer, not that you know stuff, because guess what? Google knows more. And the AI is already starting to generate what? Paintings, music, articles, and so on. So it's not about generating either. It's about problem solving, critical thinking. Those are still stuff that we can do better compared to the AI. So you had a question earlier. Go ahead. Oh, I thought you had.
Oh, no.
Oh, okay. So there you go. And I will try my best to point out what things are important as I go over those topics. So I will do my best to help out. So the other part is how are the k-bits specifically defined, and example of a basics addition. So I want to do this example in class just so that we have a refresher of how those rows are defined, what is R, what is C, and how do we use those particular functions. So that's what we're going to do now. And to do that, I have to start a few scripts on my side. Okay, so let me start it on this side. Oops. Okay. All right, so what you're seeing here is the example from the previous class. And what I'll do is I'm going to give you a new example today, but not using base 10. It's going to be using base 6. So this way we have a very good opportunity to look into how to use the R function and how to use the C function. Now, what is important here is the definition and the relationship between Q of I and Xi, Yi is already defined here. The relationship between F of I and Q of I and K of I is already defined here. The relationship between K of I plus 1 and C of X of I, Y of I, Q of I, K of I is also defined here. So this is basically a very succinct summary of what we have talked about up to last lecture. Yes?
I know it's the R and C function, but was there a reason they were called R and C during this big reason?
I cannot even remember why. C is for carry, I know that. I think R, I just cannot remember. I cannot remember why I chose to use it. Go ahead. Remainder could be a good one because it is the remainder of, in this case, the two parameters, and then divided by the base. So remainder is a good one. Yep. There are times when we come up with the acronym and then later on figure out what the acronym is supposed to mean. PHP is one. Yeah, you guys can look up all the alternative interpretation of PHP, the programming language, and some of those are fairly interesting. All right, so this is an important slide, and I'm going to move forward because I have to present an example. And I cannot remember where I put my stylus. Actually, I found it on the podium. I left it on the podium last time, but that's not good because it still has battery. Okay, so we're in business. All right. So if you're talking about absent-minded, I'm probably in the 98th percentile, meaning that about 1 to 2% of the entire population is more absent-minded than I am. All right, so let's go ahead and we'll present a new example. In fact, I'm going to start a new page. So we'll go to journal, start a new page after. So now we can get started with a new example. So I'm going to have to write down base 6 first, okay? Because what we mod with and what we compare to in the R and the C function is determined by what base we are working with. So since we're working with base 6, X, Y also has to be, I have to make sure that those digits they can only be from 0 to 5, because in base 6, you do not have 6 as a single digit. All right, so we'll go ahead and start with 2, 3, 4, okay, plus 1, 2, 5. All right, so we're gonna do this addition, but in base 6. So the first two rows are x and y. They are basically the numbers that we are adding. The next row is q. But q is really just the r function applied to x and y of the digits of a particular column. So we're going to apply that. So for this position here, can you guys see the yellow circle thing? Okay.
Yeah.
So for this position, it's going to be the r of 4 and 5. So it's going to be 4 plus 5, the whole thing mod 6. 4 plus 5 is, regardless of the, in base 10 is 9, the value 9. 9 mod 6 is 3. So I'm going to put 3 here. 3 plus 2 is 5 in base 6 also. 2 plus 1 is 3 also in base 6. Okay, because whether we mod 3 with 6 or not, we still get 3 back. Are we good so far? Do we understand how the digits of the Q row were computed? All right. So now we move on to the K row. Okay, so this is the row K, the next one. The K row is a little bit more complicated because it's the carries. So at this point, we're going to say, well, for K0, it's always going to be a 0 because we do not have any digits, lower significant digit or less significant digits compared to digit 0. So that's why K0 is always going to be 0 for the time being. Okay, so there will be some time when we say, well, that's also a variable, but not for now. Okay, that one is always going to be a 0. So whatever goes into this position here is C of 4, 5 plus C of 3, 0. How do we know? Well, because the previous page on my journal is already quoting that particular equation. So this means it is also important for all of you to get familiarized with the equations. Okay, because if you know the equations in your head, in your mind, then you can go like, oh, okay, I know exactly how to compute this particular digit here. All right, so 4 plus 5 is 9. 9 is greater than or equal to 6 is true. So the C function is going to return a 1. So go ahead. There was a question? No? Okay. So that means this is going to be a 1 over here. And now we will try to determine K of 2. So K2 is C of 3, 2 plus C of 5, 1. C of 3, 2 is basically comparing 3 plus 2, which is 5, against 6. And 5 is not greater than or equal to 6. So C returns 0. But then we also want to compute C of 5, 1. 5 plus 1 is 6. 6 is greater than or equal to 6 is true. So that returns a 1. And since we are adding the return values of the C2 invocations of the C function, so that means we have 0 plus 1, which is a 1. So the position where the yellow spot is going to be a 1. All right. So we can even compute K3. So K3 is here. It is C of 2, 1, which is 0, plus C of 3, 1, which is also 0. So we have 0 plus 0, so we get a 0 here. Now we can finally compute the actual result that we want, which is the sum. And the sum in this case is basically applying the R function to the Q and the K rows, or I should say the Q and the K values of the same column. So in this particular place here, we have R of 3, 0. 3 plus 0 is 3. 3 mod 6 is still 3. So 3 it is. And then we try to compute this one. 5 plus 1 is 6. 6 mod 6 is a 0. So we put a 0 here. Then we try to compute this one. 3 plus 1 is 4. 4 mod 6 is 4. So we put a 4 here, and we're done. Do we have any questions about the process? This process has no difference whatsoever compared to the base 9 multi-digit addition that we went through in the previous class. The only thing that got changed is the base. But the way we compute Q, K, and S remain exactly the same. So the structure of doing things is exactly the same, which is what we want in computer science, because we are trying to extract a method to do something regardless of what values we are processing. So now we have the structure. And of course, you can also say, how can we tell this is the right answer? Technically, for all we know, you're just spewing out some digits and make sure everything is between 0 and 5 and call it a day. That might have been the case. So we want to double check, right? How do we double check?
We can convert it back.
Yes, we can convert every single number from base 6 back to base 10, perform the addition in base 10 because your calculator can help you with that one, and then see if the answer is the answer. I mean, there's an off chance that I might have made several mistakes in a row, and then the errors just somehow cancel each other, but the chances are pretty slim. Yes.
We have to do the base 10 addition, then convert back to base 6, correct? Checking.
No, we just do the base 10 on the side.
Okay.
Yep, so this is also a good opportunity to kind of re-demonstrate, how to do base conversion, right? So we have 2 times 36 because of the 2 here, plus 3 times 6. Okay, let me make it clear that this is times, plus 4 times 1. So that's 72 plus 18, which is 90. And that's 90 plus 4. So this is supposed to be 94 in base 10. This one here, that's 1. Oops. Okay. 1 times 36 plus 2 times 6 plus 5 times 1. So we got 36 plus 12, which is 48. 48 plus 5 is 53. Let me just pause here. Do we have any questions about why I multiply digit 2 by 36? Are there any questions about that? Or does anyone want to volunteer an explanation of why 36 is the quantity that I multiply digit 2 to?
Is that your 6 to the second?
Yep, 6 to the second, because of the position of the digit. It is representing the quantities of 6, which is the base, raised to the power of 2, which is the position. All right, so this is the sigma notation. Okay, if you go back to the base conversion stuff, the sigma notation is responsible for how I perform those calculations. Yes?
Where did you get 36?
I just explained it. It is because this digit here, the entire column, is representing the quantities of 6 to the power of 2 because it is at position 2. So in the base 6 number, that particular digit will be representing the quantity of 6 to the power of 2, which in base 10 is 36. Is that okay? Sort of? Okay. All right, so now we go to the result. Okay, so if you want to, we can carry out the addition in base 10 and then convert it back to base 6 and see if we get 403 back. So that's a pretty good way to do the other way, because I can also demonstrate how to do base conversion. Given the value, how do we convert it into a number of a specific base? All right, so we'll do the calculation here, adding 94 and 53. So we got 7 here and then the 1/4 here. So we have 147. So the question now is, how do we represent 147 in base 10 and convert it into base 6? So the intuitive way is simply to ask, can we fit any 6 to the power of 3 here? 6 to the power of 3 is 36 times 6, which is more than 180. I don't think so. 147 is certainly less than 180, so I know there are no 6 to the power of 3 whatsoever. Yes?
Would it not just be easier just to convert 403 to base 10?
Say that again?
Would it not be easier to convert the base 6 number to base 10 and then compare it to base 10?
Yes, you're correct. But if there's a harder way to do something, I'll find it and I'll do it that way. Which is also what I expect you to do in the exams. You would laugh now. Not necessarily because it's more difficult, because I want to make sure that you guys know the process, you know how to do it, okay? All right, so what about 36? Well, I'm pretty sure 147 has some 36s in it, okay? So we'll go through the calculation. Do you guys know that division is actually very difficult to do because you have to actually be able to memorize the entire multiplication table and do multiplication mentally in order to do division quickly. So in this case, it's going to be it'll be 4, right? Because 4 times 36 is 144. So we have 4, sorry, I said 4. So 4 times 36 is 144 with a remainder of 3. So now this is the amount that is left. So we know this 4. This 4 here is confirming that there are 4 36 chunks, okay, within 147. What is left is 3. So now we ask, well, are there any 6s in 3? Nope, doesn't make sense to me. So now we can, sorry?
Half of one.
It has to be an integer, right? It has to be integral. So we have 0. We have none of those. And then what is left is how many ones do we have? Well, we just need 3 ones to take care of 3 itself. So now we have just verified that 403 in base 6 is representing exactly the same thing that we call 147 in base 10. So are we good so far? So what I have done is not just to carefully go back to re-examine every single step when I perform this calculation. Instead, I use an alternate route, okay, to exercise things that I have learned already by this time of this class to see, hey, I can probably use that method to double check this particular method here. Because even if you retrace exactly the same steps and do it very carefully, the chances are if you make one mistake, conceptual mistake particularly the first time, you're going to make the same mistake the second time. So by going through an entirely different route, I have a better chance of catching my mistakes. So are we good so far? So this is a quick review as an example of not only XYQKS, which by the way is the access code of the lab, all lowercase, XYQKS, okay? I'll say that again at the end of the lecture. So it's not just a demonstration of how we perform multi-digit addition, but it's also a quick review of base conversion, one way and the other way. Are we okay so far? All right. So now we're going to get to the portion where I would have to say, well, I mean, if you don't want to get into it, it's okay not to get into it. And once you see what I'm going to present, you will go like, okay, well, that kind of makes sense. But for some of you, that might actually be interesting. So everybody has a different standard of what is interesting and what is not. Okay, but I need to get back to Joplin. I really like Joplin because it allows me to type notes really quickly, and it does all the formulations in terms of equations, also really quickly too. All right. So the main topic of today is how we compute R and C in base 2. But before we get there, I want to show you, the result here. So let me show you what the result is first. So the result is, okay, the way we compute K of I plus 1 is this, okay? This is the way that I talked about it on Tuesday. But as it turns out, we can also do it this way. This is the OR operator, by the way, which is the same as bar in C++. So you go like, addition and OR, they're not exactly the same. They're the same sometimes, most of the time, because if you have 0 plus 0, you get 0. If you have 0 or 0, you also get 0. Right? If you have 1 plus 0, you get 1. If you have 1 or 0, you still have 1. Not a problem. If you have 0 plus 1, you have 1. If you have 0 or 1, you also have 1. So for the 4 possible cases, the first 3, which is presented here, are the same. The last row is different. Why is it missing? So the last row would have been 1, 1 here, where 1 plus 1 is 2, and then 1 or 1 is still 1. That will be the row where the addition is not going to do exactly the same thing as the disjunction. So why is that row missing? That row is missing because the previous mumbo jumbo stuff just proved that in this particular scenario, based on the constraints that we have, only up to one of the 2 C functions would return a 1. If one returns a 1, it guarantees the other one is a 0. Now, can they both be zeros? Yes, that's entirely possible. They just cannot be both ones. Is that okay? So most of the time, for many people, and I would say including professors, they would go through a few examples and go like, well, intuitively, it seems to make sense. And I'm just going to take it as granted, okay, that it is not possible for C of Xi, Yi, and C of Qi, Ki both to be ones, okay? But I need that proof. I need to actually step by step and prove it in order to convince myself that yes, there's no chance that both of these can be ones. So the proof is about, this is basically everything starting from here, scenario 1, all the way to the end of scenario 2. That is the proof of why these 2 carry functions or the 2 invocations of carry cannot both be ones. Now, do you need to know that? No, but I would think that most people should at some point be interested in knowing why. All right. So once again, the proof itself is not important, but the end result, which is C of Xi, Yi and C of Qi, Ki cannot both be ones, is important. Why is it important? Because we can change the addition to an OR. Why is that important? Because I don't know how to do the plus, okay? In fact, this entire module, binary addition, is to try to figure out how do we compute the sum of 2 binary numbers. So the plus is making this whole thing circular. But if I can convert the plus and say, in this scenario, in this very specific situation, I can also do a regular OR or logical OR. That's a good thing because we know how to implement a logical OR using transistors.
Is this the entire reason that that the plus sign is used for OR in engineering notation?
That's a very good question. So let me repeat the question. The question is this the reason why the plus symbol is also basically what is the C++ term for that? Overloaded. Is also overloaded to mean disjunction in electrical and computer engineering. The answer is sort of, okay? So the answer has to do with algebra. So plus and addition and multiplication are analogous to disjunction and conjunction in if they translate between regular algebra and Boolean algebra. Logical negation is analogous to arithmetic negation. So that's why they share the same symbols because in terms of algebra, you can do abstraction, you can do abstract algebra, and you can fold the 2 types of algebra into one single more abstract algebra. And those operators basically do about the same thing. That's the best way I can describe it without getting into abstract algebra. The same thing for 0 and 1. 0 is the identity of addition, which means x plus 0 is just x. But guess what? False is also the identity value for disjunction. X or false is x. And then the same thing with true versus conjunction. So all of this stuff here requires one more abstraction layer on top of Boolean algebra and regular algebra. So the more abstract algebra basically just says, oh, okay, we are just interested in the derivations and theorems that are common to all of these other algebras. Linear algebra falls into this category too. Certain operators of linear algebra also can be abstracted into the same algebra family. So without getting too much into abstract algebra, that's the reason why they share the same symbol. I know it's a really long answer to a short question. That's sometimes what I tend to do is to kind of do that. All right, so this part is all done, and we can now get back to the notes. So where does that leave us? So where that's leaving us is section 5. Okay, so section 5 is about how do we perform addition, using base 2 numbers, using transistors. So before we get there, I suppose we need to talk about this part here. All right, so we'll start with this paragraph here. Let me just gonna zoom in a little bit. All right, so we want to look at the R and the C function for base 2. Because we already know that function works across all the bases. Just change the 10 to whatever base you want to work with, and it's going to work. But base 2 is special. Okay, so we'll take a look at base 2, and I am going to do it using Joplin because it just looks a lot neater this way. Okay, so we'll go ahead and take a look at, so we have x, y, and then we want to look at C of x, y. And then we also want to look at R of XY. Okay, so we're going to make a table out of this. And that's how we make a table in Joplin or Markdown. X can be 0, Y can be 0 at the same time. And then we'll figure out the other 2 columns. X can be 0, Y can be 1 at the same time. And we'll figure out the rest. And then we have 1, 0. And then finally, we have 1, 1. And you guys can just focus on the right-hand side, which is this part here, as I try to fill in the values. All right, so now we're dealing with base 2. Okay, so just remember, we're dealing with base 2. So what is C of 0, 0? It's 0 for just about all the bases, right? So, that's an easy one. So we'll go ahead and put a 0 here. What about in this case? What about in 0 plus 1, do we end up with a borrow, excuse me, a carry in base 2? No, so that's a 0, 2. What about 1 plus 0? It is just being commutative, so that's a 0, 2. So this is the only time, right? 1 plus 1 is 2. 2 is greater than or equal to the base, which is 2, is true. So C is going to return 1 in the case of 1 and 1. C of 1, 1 returns a 1. Okay, well, I'm going to pause here and see if there are any questions about the column for the carry function or the result of the carry function. We good? Okay, so now we're going to work with the R function, which is basically the remainder of the sum of xy divided by the base. Okay, or you can say x plus y mod base. In this case, it's 2. So what is 0 plus 0 mod 2? 0. What is 0 plus 1 mod 2? 1. What is 1 plus 0 mod 2? 1. And what is 1 plus 1 mod 2?
0.
All right. You guys have already figured this out. Very good. So we look at this table and go like, yeah, that's kind of cool. But I think I recognize a Boolean operator for the C function. In other words, if I don't call this the result of the C function, and I just present the truth table, just this portion here, don't you think it just looks just like conjunction? It is exactly the same as conjunction. Huh. So that means in base 2, you can implement the C function using logical AND. Okay, so let me just write it down here. Okay, so because I wanted to make sure that we that I summarize what I'm talking about here. So in base 2, okay, so x plus y, the whole thing, mod 2 is really the same thing as x and y. Is that okay? So what is the big deal? That tack, because if we have one way to do the calculation already, why would we need the other way? Well, because we're trying to figure out how to use transistors, electronics, to compute addition. So if addition requires addition itself, that doesn't give me a method to implement it in logic gates. On the other hand, if I can say, well, guess what? It is also just logical AND. We know how to do logical AND out of NAND gates, and NAND gates can be made out of transistors. So indirectly, we can implement a AND gate using just transistors, maybe a whole bunch, but it is possible. All I care is whether it can be done or not. Is that okay? Does everybody understand the rationale behind why I care about this equivalence? Okay. So what about the other column? What about column 4, which is the R function? Well, that turns out to be a little bit more difficult. So let me say again?
RXY isn't that an XOR?
It is exclusive OR. Yep. Yep. So let me. So exclusive OR is not super well known to most people. So I'm going to present it, in a way that only uses AND and OR, at least for now. Okay, and also negation. So okay, let me get back here. So the mathematical way of defining this is to see if x plus y is greater than or equal to 2. And if so, we return the value of 1. If not, we return the value of 0. Okay. So this is I'm using a ternary expression to say what this is doing. It's basically saying if x plus 1 is greater than or equal to 2, it returns a 1. Otherwise, it returns a 0. If you want to, you can use the floor function to do this too. So you can use a floor function applied to x plus y divided by 2. That will give you exactly the same result. Okay, but this is what I've been using in my definition of the R function. So I'm going to stick with this one. So as it turns out, this is known also as exclusive OR. Yes.
So that I'm still stuck on the CXY.
Yes.
So when you say x plus y mod 2, you mean that as a Boolean.
Oh, that's yes, you guys are right. I flipped the thing. Yep. I did flip it. This is the x and y. That is the other one. Sorry. My mistake. And if you think this mistake is bad, wait until you watch my video for 440 because I made it even bigger in that class. I don't have a problem with admitting to my mistakes. I just have a problem of making the mistake. There's a difference. I'll let you guys think about what the difference is. Yes.
So RXY, is that like the negation of like if and only if? Like,
You mean this one?
no, the R like because actually it would be the if and only if, not the negation.
Which row are we talking about? Which part are we?
Be clear, the
Oh, okay.
fourth column is if and only if.
Yes, it is also, no, it is the negation of if and only if. It is exactly the opposite of if and only if. So if you want to use if and only if, you can do that too. But I want to boil it down all the way to negation, conjunction, and disjunction, because those are the operators that we are familiar with. So, so the way to express that, which is here, is really just something or something here. And then the first something is going to be the negation of x and y. And then the second one is going to be x and the negation of y. So if you want if you want to be absolutely clear about the ordering of the operators, this will show it. All right, so not X and Y or X and not Y is going to give us exactly the same result of X plus Y mod 2. Now, we do have a lot of constraints here. X can only be 0 or 1. Y also can be 0 or 1 in this case. Without those constraints, this does not work. But since we're dealing with base 2 numbers, X can only go from 0 to 1, Y can only go from 0 to 1. And under those constraints, these two expressions would be the same. These two expressions would be the same. Hmm?
Sorry, I was.
You know, that's a very tough question for me because once the words out is coming out of me, I cannot remember what I just said. It's not a lack of willingness, it is a lack of the ability to recall exactly what I just said. Yes.
Yeah, let's give us the time stamp to the video. Look at that.
It is 8:16, but you can't see it in the video. So what I can do, that's a good idea. I like that. So what I can do is to make a timestamp thingy. X clock. Nope, X clock. Okay, so this is going to be funny because by default, X clock shows where's the clock? Where did it go? Nope, that's not it. Oh, right here. Okay, so this is the clock and oh, it's not it cannot move on top of this thing here. Okay, so let me see. There we go. Okay, this is funny because if I were to do this last semester, one specific person in my class is going to say, can we use a digital clock instead? That individual was having problem reading a analog clock and told me, can we just stick with digital clocks? That was it. I find that kind of interesting because I did not anticipate that. So what about this class? Do we have a problem with analog? No? Okay. So I can make this stay on the screen all the time, always on top. So this way the clock is always here. So it's easier for you guys to find the timestamp and then you can just write down the current time and you're good to go. We did start the recording at about 5:30. So it will only be off by maybe a minute or two. All right, so getting back to Joplin, because I got everything in Joplin. Okay, so now we have a way to express something that was previously arithmetic, and now they are only using logical operators. Is that okay? So this is really important because now we can use LogiSim to create a circuit to perform binary addition. And that's the whole idea, because I want to show you guys how binary addition is carried out using logic gates. And the latest announcement for this class explains why this class is important. I'm not sure how many of you have read the latest announcement.
Was it that OpenAI thing?
Yes.
There was no message attached to that when you read it in
There's a bitmap.
I'm sorry, what was that?
There's an image. So,
Okay, my dark mode must have blocked it out.
oh, that is random. Oh, that's interesting. That is interesting. All right, so under the announcements, this is the last one. And that's it. So I asked the ChatGPT interface of OpenAI, what is the value of studying assembly language programming and computer architecture? And it gave me a pretty good answer. I just found it to be kind of interesting, and and I think this class of all people really should keep track of OpenAI, the ChatGPT and the progress of those things, because I think it will impact you, okay, one way or another. It doesn't have to be negative, it can be positive, but it will impact you. I'm too old, so I'm good. All right. So now, okay, so what we want to do, what I want to do is to go through a few examples first, okay? So there's one more thing I want to do, okay, because I want to make sure that we all understand the alternative ways to express the same thing. So this one here, okay, is also known as exclusive OR. So exclusive OR usually use this particular symbol to represent exclusive OR. The circle with plus is typically used to express exclusive OR. So exclusive OR is a 1 if only one side of the operator is a 1 and the other side is a 0. It's the opposite of equivalence. Is that okay so far? And exclusive OR can be spelled, if you have a programming language, it can be spelled as XOR, okay, for exclusive OR. It can also be spelled as EOR in some context. So there's just the alternative ways to specify the exclusive OR operator. All right, so time for an example. Okay, so for an example, we are going to switch back to Joplin. So Joplin on your side is here. There we go. Stylus. And let's start with a new page. So this time we're dealing with base 2. And we're adding two base 2 numbers, 1 0 0 1 0 1 plus I don't know, 1 0 1 1. Okay. And this is all done in base 2, but this time I'm going to explain this using only binary operators. Okay. So once again, we have X, Y, Q, K, and S over here. So I want to figure out the Q first, which is done by exclusive OR. So 1 exclusive OR with 1 is a 0. 0 exclusive OR with 1 is a 1. 1 exclusive OR with 0 is a 1. This is also a 1 over here. And now I have to compute the K's. This is starting with a 0. I explained that already. So now, in terms of this particular position, it's going to be the end of these 2 bits or the end of these 2 bits over here. Well, the end of the x0, y0 is giving me a 1 already. So that means k of 1, which is where the yellow cursor is going to be a 1. So when I try to figure out this position, then I need to figure out what is 0 and 1, which is x1, y1, or q1 and k1. That one is a 1. So now we have a 0 or 1, which is also a 1. So the yellow spot, which is representing k of 2, is also going to be a 1. And now we try to figure out the next place, which is here. This is k of 3. So k of 3 is based on the conjunction of x2, y2. x2, y2 is 1, 0. So that means the conjunction is going to be a 0. But it also wants to OR that with the conjunction of q2, k2, which are both 1s. So 1 and 1 is a 1. So we end up with 0 or 1. So that means here we end up with a 1 here as well. And the same argument applies to this one over here. Once we have all the k rows, we can now try to figure out the s row. So the s row is the exclusive OR between the q and the k. 0 exclusive OR with 0 is a 0. 1 exclusive OR with 1 is also a 0. This is also a 0. This is also a 0. Now, I'm not going to give it another digit. That's because when you are performing binary addition, the width of xy should be exactly the same as the width of the sum. Because otherwise, you cannot store the result back to where you got the values to begin with. Yes? K4 is just dangling. So I'll explain what is the value, what is the interpretation of K4. So I will explain that. So now we look at this and go like, okay, Jack, how do we know this is actually correct, right? Because I could have just put a bunch of zeros and ones out here and call it a day. So we'll go ahead and do the base conversion. 0, 1, 0, 1 is 5 in base 10 because it is 1 plus 4. 1, 0, 1, 1 is 8 plus 2 plus 1, so it is 11. So that means it is supposed to give me 16. And yet it's giving me a 0. What is going on here? Well, it's giving me a 0 here because I don't have enough digits to represent 16. But it has an overall carry of 1. So now the question is, what is the position of this 1 over here? It's K4, right? So K4 is in position 4, which means it is representing the quantities of 16, which is 2 to the power 4. So that carry is actually part of the result of the addition. We are simply saying, yeah, it is 0, but we have a carry of basically 16. Are we doing okay so far with the binary addition? Yes? Well, it's base conversion because in base 2, this is 1, this is 2, 4, 8 in terms of what quantity that position is representing. So we have 1 of 1, none of 2, 1 of 4. So we add up those 2, we got 5. And then we have 1 of 1, 1 of 2, none of 4, 1 of 8. So we have 1 plus 2 plus 8, which is 11. So that's why we have 5 plus 11 on the decimal side. All right. So are we doing okay so far with binary addition? Yes.
So we do have the 0 here, and we overflowed out to completely separate.
Yes. So what the computer remembers after a computation, this is the portion that it does remember. It remembers this part here, which is the sum, but it also remembers the overall carry. So there's a place in the processor to remember that extra dangling carry thing because it is useful for many purposes. The input to this entire thing, so let me just gonna use a different color. So these two are the inputs. Everything else are intermediate except for the things that are circled or enclosed in green. Those are the output of binary addition. Yes.
Sum is 1, 0, 0, 0, 0, numbers, right?
No, the sum is 0, 0, 0, 0 with an overall carry of 1. So that's how it is exactly represented. It does have a result of 0, 0, 0, 0 with a overall carry of 1. Yep.
So, Q is X4 for XY, and then K is for XY and K, and then S is X4 for TK.
Well, you can still apply the R and the C, except in this case, the R is computed using an exclusive OR gate, and then the C is computed using a conjunction. So we are basically, instead of using arithmetic operations for C and R, we just figure out how to use Boolean expressions to do exactly the same. So from your perspective, it is probably better to remember we're still applying the R and the C, except the way we perform the R and the C is not only using Boolean operators. We do not need to use arithmetic operators.
C is conjunction.
C is conjunction,
And
just an and, yes. And that is derived by the truth table that we talked about in Joplin. So in Joplin, that's how we figure it out because where's my mouse cursor? There we go. So in Joplin, we figure out that this column here looks exactly the same thing as a conjunction. And then this column here looks exactly the same as a exclusive OR. So that's how we figure out and go like, oh, so to compute C of XY, we can just do a conjunction. And then to do a R, we can just do the exclusive OR, or you can do the kind of more complicated one using just and, or, and not. Yes.
It's the input width and the output width you have to match.
Mhm.
Like for the result that we got, we have a carry of 1, how would we express that in the logic sum if they have to match?
Well, you just use a different output pin. So you have one output pin for sum, which is this portion, and then you have another output pin just for that one single bit. We basically separate the sum from the overall carry bit. So there are two outputs coming from the adder. One is the sum, and then the other one is the overall carry, which in this case is K4. Yep.
So here, like, we have a 4-bit adder, but we're making a 3-bit adder, right?
Mm-hmm.
So instead of having this, we would have like one of those cut off technically. And do
Yeah.
a carry bit.
All right.
Show up on your computer.
Hmm?
Show up on your screen and output. This is zero.
Not sure what you mean by that. Can you repeat the question, please?
If you try to add 5 plus 11, while using 4 bits.
Mm-hmm. It will tell you the sum is 0, but with an overall carry of 1.
That'll show up on your screen.
Well, I don't know what's going to show up on the screen because this is inside the processor. What shows up on the screen is after a lot of processing. So you can have a processor that can only process 4 bits at a time, but there are ways to process integers that are 8 bits wide, 16-bit wide, 30-bit wide. So unless I know exactly how your integer is represented and how many bits it's using, I cannot tell you what it's going to be outputting. And then also, the outputting it's already going through a lot of stuff. So when you use cout, and then less than, and then an integer variable, it's already going through base conversion because cout, unless you specify in hexadecimal or some other base, cout by default outputs what? Base 10. And that's because all of those conversion is already done behind the scene, and you just don't know that it's going through all kinds of calculations to give you the base 10 representation on the screen. Yep.
So what do how do computers use this? Like, what's the use of finite differential?
It's a very good question, and yes, there's a long answer and there's a short answer. The short answer is the computer uses a binary addition mechanism to add numbers.
What is that for? Like, just one process. Like, I'm confused.
Well-
Other than like a calculator.
Okay, so a computer can do a lot of calculations, but all the calculations boil down to, okay, I can try to remember how the few operations. You have addition, subtraction, comparison is kind of subtraction. We'll talk about that later. You have right shifting, you have and, bitwise and, bitwise or, bitwise not. Those are the very basic operations that the processor needs to know how to do in order to do everything else. So your complicated C++ program, your MP3 player, okay, all the cool stuff that you use a computer for, all of those calculations can boil all the way down to addition, subtraction, comparison, bitwise and, bitwise or, bitwise not. And I'm pretty sure you don't need both bitwise and bitwise or, because your one can be derived from the other one using bitwise not. So yeah, so we are basically talking about the most basic mechanism here to do all the computations that your computer can do. So all the other stuff like log, exponent of, sine, cosine, tangent, and whatnot, they all boil down to these really, really elemental operations. Yes.
So then all of these operations, they also boil down to like NAND. So
Yes.
that's where we're going. We're gonna keep going up in second class, right?
Right. Yeah. So they all boil down to NAND gates, or at least we know how to boil everything down to NAND gates, which then boil down to 2 p and 2 n type transistors. So the idea is, yes, we can use semiconductor to do it. Okay, and also remember the P and the N type transistors is really just the technology that we have now. If you can have a valve or a gate technology using hydraulics that has the same property of using water pressure as the gate to control the flow of the hydraulic fluid going in one direction and then the other one to control in the opposite direction, you can make a computer out of hydraulic valves or air valves and so on and so forth. It is not so much the physics that is important. It is the property of the switches that is important. So that part is kind of interesting because we really do not have to have electronic computers. So if you think about what if there's a nuclear blast and all the semiconductor would go bad? Well, switch to hydraulic computers. And then, sorry? It will work the same except extremely slowly. Because a transistor is nothing more than a valve, okay? You have one input that will only take a little bit of a pressure in the case of a valve to control a diaphragm, which then switch a larger volume of flow of the hydraulic fluid. So what you need is a P-type transistor that turns on when the input is low, and then you need an N-type transistor that turns on when the input is high. As long as you have those two types of valves, you can make a computer. You have your basic N and P transistors. You can hook it up the same way that we hook up our four transistors, and then you still end up with the same logic gate, except it is not expressed in voltage anymore. It is now expressed in hydraulic fluid pressure. And that will be immune to the EM, electromagnetic interference, EMI effect of nuclear bombs. But it'll be very slow. Sorry?
Let's hope that doesn't happen. The apocalypse, close to apocalypse.
Well, the zombies will have to operate that hydraulic computer, right? Which means they will get a lot of zombies. They'll turn in a big crank, in order to kind of act as the pump, to provide all the pressure, for the whole thing to work. I can see a science fiction coming. You guys can become famous and rich because now you can go to is it Midjourney, the engine that can paint based on the prompt. So now you can have your own graphic novel of zombies operating a hydraulic computer post nuclear war. Isn't that cool? What does that have anything to do with assembly language programming and hydraulic and computer architecture? It doesn't depend on electronics. You can use similar switch technology based on the polarity of pressure, no pressure to turn on the valve or turn off the valve. As long as those properties are preserved, you can make computers out of a lot of different media. So I think that part is kind of interesting because that's a it's one way to look at computing. All right, so let's take roll because I almost forgot to take roll. So and I put some time into today's roll taking activity because I'm switching to a new quiz type. So let me show you what it looks like. It looks a little bit different, but it's kind of the same thing. Oh, I need to get out of my student view. Because otherwise I won't see it. All right, so today is the 26th. This is the roll taking activity. I'll show you the passcode first, but you know that already. Some of you still remember because you took notes, and for the rest of you, because you did not, you won't know it. Okay, so this is slightly different compared to the previous one. You cannot see it yet. I have not released it yet. All right, so when we get to here, we go to settings. It's a little bit different. Oh, I thought I specified. The access code, so it's not specified here. All right. So where is it specified? Okay. So. All right, so. I cannot remember, how I specify the access code. Huh,
I think it was in that last meeting you were in.
sorry,
I think it was in that last meeting you were in.
the last screen? Yeah, I think so. Let me do it one more time.
Oh, you also need to change the date.
Right, yeah, well, you guys cannot see it yet because I have not published. So let me publish first. It's, and I'll give you guys what, till the end of today's class period. So that would be 6:50 p.m. 6:50 p.m. Save and publish. And I'm pretty sure the access code is XYQKT. And the best way to show you that is here. It would be lowercase XYQKS. Let me see, let me know if it doesn't work.
There's no access.
There is no access.
There's no access code? It's okay. I thought I set it up because it's a new quiz interface. But that's okay. I mean, as long as you guys check in and go like, yes, I am in class, that's fine. Yeah, this is kind of important that I keep track of row taking because the college gets funding based on enrollment, right? So one way for the college, if the college is not abiding by the law, the college can generate a lot of virtual students in a lot of classes and then show the state and go like, look, we got all this enrollment. We got all of these students. Give us money. When there are actually 5 people sitting in the class of 60 in double quotes, right? So that's why it is important for me to take roll so that we actually, I can show the college and also the state chancellor's office that, yeah, we actually got people here. All right, so we only got about 8 minutes left, which is more than enough time to start to talk about, how to put an adder together in LogicSim. So that's what I'm going to do next. Your lab does not have to do with that portion, so you don't have to worry about using LogicSim today. So I am going to start up LogicSim. And that's going to be Java -Java. So here's LogicSim. All right, so we're gonna do a 3-bit by 3-bit adder, okay? So we'll go ahead and pick out an input pin for X, and we'll make it 3-bit wide for X, and then Control D duplicates. So now we have another input pin, and I'm going to call this one Y. All right. So the fun part of doing this is, do you remember all of the qubits? They're all exclusive ORs of the respective X and Y. What do you mean by that? Okay, that means the cube of 0 is the exclusive OR of X0, Y0. Cube of 1 is the exclusive OR X1, Y1. Cube of 2 is the exclusive OR X2, Y2. So instead of using a splitter, we split all of those bits out and then use 3 individual exclusive OR gates to do all of that stuff. I can now use a multi-bit exclusive OR gate to do everything at the same time. So that is kind of cool. So we'll go to the gates here, pick out the exclusive OR gate, which is XOR in this case. Looks too big, turn it into a smaller one. We only need 2 inputs. And it's going to be 3-bit wide. So data bits is going to be 3. And I only need 2 inputs. I forgot to change that one. There we go. All right, so now I can compute all of the qubits all at the same time. So whatever comes out of here would be all the Q bits, which is really cool. But now we need to compute the K bits. The K bits is kind of a problem because it's staggered. K of 1 depends on x0, y0, q0, and k0, which we can assume to be a 0 in this case, but we can also have an input pin to represent k0. But the point is, there's no easy way for me to use a multi-bit gate to handle that. So this is k0. So that means, I now need to use an AND gate, and we take the bit 0 here, and that's one component. So we can use an AND gate, sort of like what we did with the other one. So we have a 3-bit narrow 2-input AND gate here. And we can AND all the X and the Y together. So basically we have X, which is multi-bit, and then we have Y, which is also multi-bit. So the output coming out of here has no specific name, because the output here is really just x0 and y0, which is used to compute k of 1. But that's only one component of k of 1. It also has x1 and y1, which is used to compute k of 2, but it's only one of the components to compute k of 2. So I can only go so far, in terms of using a multi-bit gate here. It's 46. I still have some time, so I can still continue to work on this. And then next time on Tuesday, I can kind of show you the finished work here. But I can also show you why this is not the best way to do things. It will get the job done, but it's not the best way to get it done. So I'm using a gate here. A splitter. I need a 3 fan out and 3-bit. So now I can now separate. This Y here is corresponding to x0 and y0, and this Y here, that's x0 exclusive OR with y0, which is q0. So what do I need to do now? I need to somehow compute q0 and k0. So where do I find q0?
But you have to split off that
Yep.
port.
Yep. Okay, so we'll go ahead and duplicate the splitter so that this is basically q0, q1, q2. This is k0. So now I need an AND gate to AND these two together as one component, and then OR that with this one over here. I'll finish this part, just this part, and then on Thursday, I'll finish up the entire thing, because I do want to finish at least this portion. So I'll need a simple AND gate that's just using 1 bit in the input. No, 2. There you go. All right. So this AND is going to take K0 as one of the inputs. And it's going to take, this is Q0, okay? By the way, this is Q0. So now we have Q0 and K0, which is one part of K1. The other part of K1 is coming out of here, which is X0 and Y0. And then these two need to be ORed. So take out an OR gate and do exactly the same thing. Make it a smaller one, only with 2 inputs. So now I need to OR this thing here with this thing over here. And then whatever is coming out of here is now K1. So I need to do the same thing with K2 and then K3. And then once I have all the Ks, how do we compute the S? That's exactly what we talked about today. How do we compute the S bits using the Q and the Ks? Another exclusive OR, another exclusive OR. So I don't have time to finish this entire design today. So on Thursday, I will go ahead and finish it. Yep.
I just wanted to make it a little note while I thought here, but Matt Parker is a math comedian, I guess. He did this with dominoes, with binaries. It is in sort of thing. He put it in the video and this one.
Okay,
Yeah.
all right, thank you.
Not Parker, is awesome. His YouTube channel is Stand Up Math. Highly recommended.
Okay, the question is, did he do one for Carrie Look Ahead Addict? Because that's what we're gonna do too, is a Carrie Look Ahead. And right. There.
Do we have a lab code today or?